In section 3.2, we're going to take what we learned about the chain rule and we're going to apply it to some other derivative rules. We're also actually going to use it to discover a couple new derivative rules. So we're going to start just with e to the x. So we know the derivative of e to the x is e to the x. If I need to apply the chain rule, though, if I have the derivative of e to the u, and u is a function of x, in other words, it's not just an x up there, but it's got a function of x up there, so it's a composition of functions. Then I take the derivative of e to the u, still e to the u, times by, and I have to multiply it by the derivative of the inside of the function. Well, the inside is the power now, so I take the derivative of u. We know the derivative of ln of x is 1 over x. So if I take the derivative of ln of u, and u is a function of x, again, it's not just an x in there anymore, we've got a function of x, then I end up with 1 over u, but I have to times it by the derivative of the inside. That's your chain rule, right? Times it by u primed. So a lot of times when you could just write it this way. Really what happens when you take the derivative of the ln of u is you end up with u prime over u. So the derivative of the inside on top, the inside on the bottom. So let me show you a couple of examples. If I had e to the 2x plus 1, and I wanted to find the derivative, y primed. So now I just don't have an x up there, I have a function of x, right? This is my inside. If you want, sometimes it helps to put parentheses around that. The 2x plus 1 is the inside function, and the e to the power is the outside function. So when I take the derivative of the outside, it just stays the same. It's still e to the 2x plus 1. But I have to multiply it by the derivative of the inside, and this is the inside of the function on an exponential. So the derivative of 2x plus 1 is 2. So y primed equals 2e to the 2x plus 1. Let's do one with the ln. Let's say we'll do the same thing. Let's say I have the ln of 2x plus 1. So now I've got my outside function, which is the ln, my inside function, which is the 2x plus 1. I've got to do chain rule. So when I take the derivative, I'll call that y again. Y primed is equal to 1 over 2x plus 1 times by the derivative of the inside. Well, the inside is 2x plus 1, the derivative is 2. Well, when you multiply those together, you just end up with 2 over 2x plus 1. So the shortcut up here, what it's saying is, if I just take the inside and put it in the denominator, and I take the derivative of the inside, derivative of 2x plus 1 and 2, and put it in the numerator, I have my answer, just 2 over 2x plus 1. Something else we did is, or something else we talked about if you were here in class, is someone brought up that when we found out the derivative of e to the x was e to the x, someone asked, well, what about bases other than e? Well, we're going to discover that right now. So I'm going to go through and show you where this derivative rule comes from. You'll never have to reproduce this. I just want you to understand where it comes from. So I don't know how to take derivative of a to the x, so I'm going to rewrite it this way as e to the ln of a to the x. Well, e to the ln are inverses. They undo each other, which really means this is still really just a to the x. Just looks different. So the next step is I'm going to go like this. I'm going to go the derivative of, and I'm going to rewrite it one more time. I'm going to say it's e to the ln. Well, sorry about that. I'm going to write it as being e to the x times the ln of a. So I just dropped the x down in front. That's one of our rules, right? Our logarithmic rules. An expanding is we can drop an exponent down in front. Okay, now I'm actually going to take the derivative. So let's use that rule we just did. So if I'm taking derivative of e to the x ln of a, the e to the x ln of a stays the same, but I have to multiply it by the derivative of that. Well, ln of a is just a constant. Okay, it's a coefficient, right? Just a quick example. If I have 5x, derivative of 5x is just 5. Or if I have 10.2x, derivative of 10.2x is just 10.2. So if I have ln of ax, ln of a is just a constant. The x goes away, so the derivative is just the ln of a. So if I come back up here, when I take the derivative of x ln of a, that is just the ln of a. Okay, that is my derivative then. The derivative of that comes out to be that. So that's our rule is, oh, one last thing, I'm sorry, I'm not done. I'm going to take that x and move it back up there. So now I would have e to the ln of a to the x times the ln of a. E to the ln cancels out. Sorry, that's all the way simplified down is if I take the derivative of a to the x, it's still a to the x, but I have to multiply it by the ln of a. So If it's base e, I don't have to worry about this step. If it's any other base, for example, base 2, then I'd have to times it by the ln of 2. Or if it's base 5, times by the ln of 5 when I take the derivative. You're not going to have to prove that or show any of that. You're just going to have to know the rule, right? This is just adding to those list of rules that we know, right? So if I take the derivative of a to the x power, it comes out to be a to the x times ln of a. If there's a function of x up here, so u is a function of x, then I'm going to have, right, a to the u still, but I have to times it by the derivative of my power, derivative of u, and I still have that ln of a off to the side. Okay, last new rule is if I have the derivative of log base a of x, this is one of the reasons why way back in chapter 0 I said you got to know these logarithmic properties. You can rewrite a logarithm in ln form. So log base a of x you can write as being ln of x over ln of a. That was a change of base formula. So I don't know how to find log base a, so I'm going to show you, I'm going to rewrite it as an ln. So I'm going to rewrite it as being d dx of the ln of x over the ln of a. And the reason why I did that is because I know how to find the derivative of the ln. Okay, now I'm going to take it and rewrite it one more time. I'm going to write it this way as the derivative of 1 over the ln of a times the ln of x. The reason why I did that is because 1 over the ln of a, that's just a scalar multiple. That's a number. There's no variables in there. X is our only variable. So when I take the derivative, the 1 over the ln of a just stays the same, times by, and all I have to do is take the derivative of the ln of x. The derivative of ln of x is 1 over x. So long story short, I come up here, the derivative of log base a of x is equal to 1 over x ln of a. So this rule is really similar to the last one, right? If I take the derivative of a to a power, I end up with at the times by the ln of a. If I take the log of a different base, then on the bottom I have to end up with the ln of a. So instead of timesing by the ln of a, you times by the ln of a on the bottom of the fraction there. So here's our rule. Again, you're not going to have to reproduce that. In the end, you're just going to have these rules memorized. So we're just adding to that list. So if I take the derivative of log base a of x, it's just 1 over x times the ln of a. If you have a function inside of the log, so you have the composition of functions, then you need to add the derivative up on top. So let's look at some examples where we apply these. So we're going to start with this first one, number 1, f of x equals e to the x squared plus 3x. So I'm going to go f prime of x is equal to, and you have e to the x squared plus 3x. That part stays the same. You have to multiply it by the derivative of the inside. This is chain rule. Well, the inside is the power. So the derivative of the power is 2x plus 3. We're done. For number 2, it says g of x equals the ln of 3x. Just use the derivative of u equals u primed over u. Okay, so let's do that. So our rule, if you've got a function inside of the ln, that goes on the bottom, and the derivative of 3x goes on the top. You can actually simplify that, right? The 3 and the 3 simplify. You can simplify it down to be 1 over x. Let's look at number 3. It wants us to do the same problem, but now it wants us to use the properties of logarithms. So if you remember, if I have the ln of 3 times x, you can take that and separate it. You can write it as being the ln of 3 plus the ln of x. That's called expanding the logarithm, and we did that back in chapter 0. So let's do that. So I'm going to rewrite g of x as being the ln of 3 plus the ln of x. Okay, find the derivative. G prime of x is equal to, hey, the ln of 3. Ln of 3 is just a constant. It's some number. I don't know. You could plug in a calculator to find it. But when you take the derivative of a constant, it just comes out to be 0. Plus, we're going to take the derivative of the ln of x. Hey, well, 0 plus 1 over x is 1 over x. Hey, we got the same thing. So when you have a logarithm, that's one strategy. And I'm going to do an example a little later on where you'll see where that really pays off. But if you have a logarithm, you can try expanding it first before you take the derivative. A lot of times that makes it easier. Okay, let's look at number 4. So I want to take the derivative of the ln of t squared plus t. So again, when you go to take the derivative of an ln, so y prime equals the t squared plus t goes on the bottom. And then the derivative of t squared plus t goes on top. We're finished. Number 5, you're still going to use, we got an ln there, but in this case, those are times together. So we've got to use the product rule. So h prime of x equals my first x times the derivative of the second. Derivative of ln of x is 1 over x. Plus the second, ln of x, times the derivative of the first. Derivative of x is 1 times by 1. We could simplify a little bit here, right? That'd be x over x, which is 1 plus ln of x times 1. It's just the ln of x. There's my answer. There's h prime of x. Number 6, this is an exponential, right? E to a power. So I'm going to go g prime. Well, I'm going to first, this will be helpful for us, and I'll show you why. I'm going to have to take the derivative of the power. So I'm going to rewrite the power as being negative 3t to the negative 1. Okay, so now take the derivative. G prime of t is equal to the e to the negative 3t to the negative 1 stays the same. If you've got to multiply that by the derivative of the power. So let's take the derivative of that. Drop the negative 1 down. Negative 3 times negative 1 would be 3. And subtract 1 from the power. Okay, that's my answer. Now we could do a little bit of simplifying here. Like if this were free response, I would just stop. But if it's multiple choice, I'll probably simplify it. So I'm going to rewrite it as being e to the negative 3 over t. And then I've got times 3. And I'm going to move the t to the negative 2 down to the bottom. I guess you could put the 3 out in front if you wanted. Anyway, that's probably about as far as we can simplify that one. Okay, let's look at number 7. So we have f of v equals 3 square root of v. So again, I know I'm going to have to take the square root of that. So I'm going to take the derivative of that square root. So I'm going to rewrite that as being f of v equals 3v to the 1/2. Okay, so I'm going to go f prime of v is equal to the 3v to the 1/2 stays the same, times by the derivative of the power. So I'm going to drop the 1/2 down, 1/2 v to the negative 1/2, times by, this is a tricky part, is make sure you recognize this is not a base e, this is a base 3. So whenever that happens, you've got to multiply by the ln of 3, by the ln of whatever your base is. Let's just try doing a little bit of simplifying there. I have 3, I'm going to write it square root of v again, times the ln of 3 over, we got that 2 down there, and I'm going to move the v to the negative 1/2 down there. So you can rewrite that whole problem like that. Just a side note on that, we've talked about this, but make sure if you are taking the multiple choice parts, usually your answers are going to be simplified. If you're doing a free response, though, you should not ever simplify it because it's not going to help you any. The only thing that will happen is if you make a mistake on the simplification process, you'll lose points. All right, I'm going to run through this really quick. This is going to kind of just, there's a big point here. We're going to talk about it down below. I'm just going to kind of explain it really fast. If I want to graph y equals ln of the absolute value of x, start by graphing the y equals ln of x. Remember, it's the inverse of the exponentials. Exponentials cross at 0, 1. So ln's cross at 1, 0. Exponentials have a horizontal asymptote. That means logarithms have a vertical asymptote. Normally exponentials, you have the point 1. In this case, it's base e, so 1e. This one has the point e1 then, which is up there. So y equals the ln of x looks something like that. What we want to graph is y equals the absolute value of the ln of x. So remember, if you put the absolute value on the inside, it erases the left side of the graph, which doesn't matter here because there's nothing there. And you take what's on the right side and reflect it across. So let's reflect that across. You're going to have a point there. You're going to have a point there. And it's going to come up like this. Okay. So there's the graph of y equals the ln of the absolute value of x. So if you look at it, the derivative of the ln of x, as long as x is greater than 0, nothing changed, right? This y equals the ln of x was exactly the same as y equals the ln of the absolute value of x. So as long as x is greater than 0, the absolute value doesn't change anything. Your derivative is still just 1 over x. So the question is, what happens if x is less than 0, though? One thing I want to remind you of is 1 over x looks like this on the right side. Right? That's the derivative. That's what the derivative of the ln of x looks like. So each of these points, notice how all your y values are positive? That's because your slope is always positive over there. What I want to remind you of is what happens when you look at the left side. So if I come over here, now instead of your slopes being positive over here, your slopes are always negative. But if you compare them, this slope and this slope on either side, it's the same, only this one is positive. Whoops, sorry about that. That one is positive and this one is negative. Same thing here. That point and that point will have the same slope, only this one is positive over here. This one is negative over here. Well, if you remember what y equals 1 over x looks like, the left side of y equals 1 over x is just like this. It has exactly the same y values as this one. The difference is these are negative and these are positive. So anyway, long story short, I know this was a lot to it, it's kind of confusing, but long story short is when x is less than 0, the derivative of the ln of x is still 1 over x. So all of that, if we could sum all of that up, I know it's kind of confusing. Hopefully it kind of made sense and kind of helped us to finish. But in the end, this is what you have to know, is when you differentiate the ln of the absolute value of x or ln of the absolute value of u, this is the part you're going to circle or highlight and put a star by. The absolute value, you can just ignore it. The ln of the absolute value of x is the same thing as the ln of x that we've already done. They're exactly the same. It does change the domain of the function, so it changes the domain, but it does not change the derivative. The derivative is going to be exactly the same. Let me actually, for some reason, when I went through these examples, it did not show example number 9. So look at example number 9. I'm going to write it down here, and then we'll do it together. So there's example 9, just magically appeared, right? So I want to take the derivative of the ln of the absolute value of 5 minus 2y cubed. So this whole thing we just set up above is just that absolute value doesn't change anything as far as the derivative goes. So the derivative is still going to be, put the 5 minus 2y cubed on the bottom, and then take the derivative of that and put it up on top. So the derivative of 5 would be 0, minus 2y cubed would be minus 6y squared. So again, long story short, you can just ignore those absolute values inside of the ln when you're finding the derivative. It does change the domain of the function, but it's not asking for the domain, it's asking for the derivative. Okay, I just have a couple last examples here. Let's start, oops, sorry about that. Let's start by finding this next derivative, and this is another really important point. So grab your highlighter or whatever. This is really important. When possible, you want to expand logarithms before differentiating them. So if you look at this example number 10, I have ln of x times the square root of 2x plus 1 divided by x squared plus 1. If you try taking the derivative of this, it's going to be really difficult. It's going to be kind of a disaster unless you first expand the logarithm. So remember what expanding the logarithm means. It means taking it and breaking it into separate logarithms or separate pieces. So when I do that, right, I'm going to go y equals the ln of x, and then those are times together right there, so I'm going to add plus the ln of, and I'm going to write the 2x plus 1 to the 1/2 power instead of a square root, minus, and we minus because we're dividing, the ln of x squared plus 1. If you need to review this is back in chapter 0. This is our rules for expanding logarithms. I'm going to do one last thing. I'm going to write y equals ln of x plus, I'm going to take this 1/2 and drop it down in front. We actually used that property earlier, but that's one of our properties for expanding logarithms. Well, what we just did is we took a really difficult problem, and by expanding it and breaking it into pieces, remember now I can do it term by term. I can do each of those separate. So let's find y prime. So all I do is start right here. What is the derivative of the ln of x? That's just 1 over x. Plus 1/2 is a scalar multiple times the derivative of, and what's the derivative of ln of 2x plus 1? Well, the 2x plus 1 goes on the bottom. The derivative of 2x plus 1 goes on top. That would just be 2. Minus x squared plus 1 goes on the bottom. Derivative of x squared plus 1 goes on top. Okay. And that's really my answer. We could simplify a little bit, like those two would reduce. But that's really it. And I got my answer. Now, if you don't break that apart, that problem becomes almost impossible, or at least it becomes so complex that it's really difficult to deal with. So that's really important. If you have a logarithmic problem, you're asked to find the derivative, always look first and see if you can expand it, if you can break it apart to make it simpler. All right, let's do this last problem. Sorry I didn't get these last couple erased here. So it says, what is y equals log base 2? If y equals log base 2 of x squared plus 1, find y prime of 2. So we want to find the derivative and plug 2 in. So let's find the derivative first. Hey, I want to point out, this is really important. Make sure you recognize when your base is not e. Like, this is not an ln problem anymore. So we've got to add something to that. The first part's the same, though. When I find the derivative, the x squared plus 1, the inside goes on the bottom, and the derivative of the inside goes on top. But now I have to multiply the bottom by the ln of 2. The reason why is because it's a base other than e. If it's base e, we don't have to worry about that. Any other base, you have to add that on there. Okay, now it wants me to plug 2 in. So y prime of 2 is equal to, 2 times 2 over 2 squared plus 1 times the ln of 2, 4 over 5 ln of 2. Okay, we've got that all worked out. Okay, so again, we're adding to those rules, and we're going to keep adding. So make sure, add to your flashcards. Make sure you add these new derivative rules we just went through. What happens if you have a base other than e on exponentials and logarithms? Make sure you know that the ln of the absolute value is the same as just the ln. The derivatives are the same. That doesn't change anything. And then just lots of practice. Good luck.